Hello folks, welcome. So I figured that we'd start today on the next portion of our tour through geometry here with a little bit of a problem here to start off with. So let's take a look at each of these first two problems here. And again, go ahead and pause it, try it out on your own, and then resume when we're ready to begin. Okay, so it's pretty clear in the first situation. We have Billy taller than Jamie, and Jamie's taller than Pat here. So in our first situation, right, we can go ahead and draw our people here. And again, I'm not going to draw very well here, but that's okay. Billy's taller than Jamie here, right? And then we have Jamie being taller than Pat, right? So, I hope you remember that taller here being, of course, means that has a greater height in this situation here. So it's pretty clear that if we were to draw this out, it looks something like this here. So we know that's going to be Billy. So if we're going to go down in order here, right? If we're going to go, they say that this is shorter here. It's pretty going to be Billy than Jamie than Pat. That makes sense here, right? So note that we can kind of have this sort of setup here. And we'll talk about why that's going to be the case later on. Now in problem 2, on the other hand, that's going to be a little bit different, right? Because problem 2, we have Billy is taller than Jamie, right? So again, we have that same setup here. However, now we're also told that Pat is taller than Jamie here. So notice how there's a slight difference. We swap the order of this here. And that actually changes things up significantly, right? Because if we look at Pat, we know Pat's going to be somewhere above this. So let me go ahead and sketch this here. So this is the dotted segment here. This is going to be Jamie's height. Pat's going to be taller than this, but we don't know how much taller. Because if Pat is only a millimeter taller than Jamie, then Pat's going to lie between Billy and Jamie. But if Pat is 30 centimeters taller than Billy, then Pat is going to be taller than Billy, and is going to be taller than Jamie. So notice how in this situation, see, because we don't have enough information, we can't figure this out here, right? We don't know what this ordering is going to be like here, right? We don't have enough information. So notice how in this situation here, this first one, even though technically we weren't told directly the comparison between Billy and Pat, we were able to determine it from the information given here. Here, we don't have that situation here, okay? So today, what we're going to be doing here is we're going to be focusing on the beginnings of geometric inequality, right? Because if we think about what's going on here, everything we've been doing so far has been with congruence, inequality, and everything's all honky-dory and things like that here. But of course, there are certain situations in geometry where things will not be the same, things will not be congruent. That's perfectly okay. And you'll note that it has actually developed as robustly as our congruence here. So we can actually write it up slightly differently here. So the nice part about what's going on in these sorts of things here is that many of our postulates from basic geometry here actually work very well in inequalities. So for instance, as you know about the partition postulate, right? If you have a segment here, the whole is going to be equal to any of its parts here, right? So if you have something like this, for instance, let me go ahead and do that here, right? If we have A, B, and here's C, we know the partition postulate that tells us AB equals AC plus CB here, right? We know that's the case here. However, note that in this situation, we're going to be dealing with inequalities here. Now, one thing to note about this, I'm just going to mention this right now with inequalities, we're going to be dealing with equality here, so there's going to be not a lot of congruence here. We're only going to be dealing with equality here. Furthermore, we're going to deal with strict inequalities. So when I say strict, I mean we're only going to be using this and this, okay? We're only going to be using greater than or less than. We're not using greater than or equal to here, really much. Okay, so we have AB is greater than AC plus CB. Or AB is equal to AC plus CB, I apologize. So we should be able to change this up so it says greater than instead. So presumably here, because none of these lengths are 0, we can say, for instance, that AB is greater than AC, right? So this allows us to conclude that AB is greater than AC, for instance. Or another thing we can say is AB is greater than CB here, right? So notice how what we can do is we can go from this down to either of these two things here. Both of these are perfectly valid statements. So what we currently have is our current basic postulate says the whole is equal to the sum of its parts. So now we can say that the whole is greater. We can now say that the whole is greater than any one of its parts. Okay. So the basic postulate here is that the whole is greater than any one of its parts. So this is a version of the partition postulate that gets imported into inequalities here. So you have to be kind of careful about that. Okay. Now note here, ladies and gentlemen, we can actually continue with this here, right? if we have a segment AC, we can take a look at the next major thing that we're going to be looking at. That's actually going to be important to us later on. We're going to be looking at something called the trichotomy postulate here. Okay, so trichotomy sounds very, very strange. It's sounds like a surgical procedure almost, right? But okay, let's break it down here. If we look at the word trichotomy, well, we see tri means three. And maybe you've seen this word cotomy before, at least this word root from dichotomous key from biology, where you split things up by yes or no questions, right? You're asked about a specific thing, and the question, for instance, one level of the tree will say, okay, does this thing have wings? Yes or no. And then you can divide it into two distinct categories here. So notice that we're actually going to do something very similarly here, but instead of two, we're going to do it three. So for any two real numbers a and b, exactly one of the following is true here. So if you have a segment AC like this, right, and you draw a new segment here, there are exactly three things that could happen. You could have been very lucky and drawn a segment that measures exactly the same as AC, sure. Or you could have created a longer segment, or you could have just created a shorter segment. So that tells us that the trichotomy postulate tells us this here. So we can see that the trichotomy postulate tells us exactly one of the following is true. If A is greater than B, or A is equal to B, or A is less than B. So exactly one of the following is true. Now, again, this may seem like that's just there. You're right, it does seem kind of boring and dull, but it turns out to be an important part of real numbers here, and that's actually going to be something we'll look at later on. For those of you who have done Algebra 2 or have looked into Algebra 2, I'd like you to consider that not everything has this trichotomy thing here. In particular, for those of you who know your Algebra 2, consider the following here. You know what I is, right? I being the square root of -1. So let me ask you this. Is this a true statement? I'd like you to ponder that, and we can talk about it in class if you like. Okay? Anyway, so we also note that there are other postulates that can be imported very easily into our into inequalities as well. So for instance, the transitive property. So the transitive property inequality holds up pretty well, right? We can see that if A is greater than B is greater than C, then A is greater than C. This goes back to the first situation here where we had Billy, Jamie, and Pat. Even though technically in that first situation we had no direct comparison between Billy and Pat, we were able to do that here because Jamie was sort of the middle person here. He was Jamie was the middleman here, so to speak, to connect Billy and Pat together. So we kind of have this here. Note we have the transitive property, and we also have, in addition to the transitive property, we also have the substitution postulate. And that the substitution postulate, well, you can substitute any object where it's equal in this inequality. So we add a new person to our mix here. Let's say we added Dave, and Dave was as tall as Pat, right? We can swap Pat for Dave, or Dave for Pat, and it'll be exactly the same idea here. We can do all the same comparisons here. Now, note, ladies and gentlemen, there's a big difference here between substitution postulate and transitive property. That's going to be really important to us here, okay? Substitution postulate, remember, you're swapping equals for equals. So there's got to be an equality showing up here. So something like this here, like if you have A is greater than B and C equals B here, these two together will allow you to say A is greater than C, because you can swap B for C here. That's the substitution. So notice how substitution postulate here has two different things here. One inequality, one equality. Whereas a transitive property, as you can see here pretty clearly, there are two inequalities here, and you want to make sure that you see the difference between the two. Here, we have to be very careful about the distinction because they are indeed distinct of one another, and we must respect that.